In this tutorials, we will focus on conditional expectation. Motivation. To begin with, why do we want to study conditional expectation? We may first take a look at this situation. Assumes the outcome is GPAs and the condition is time spent per week on study. Your possible questions could be, what is your expected GPAs under different conditions of time spent? For example, you may want to know the equation relating to the expected GPAs and time spent. And other questions could be, how do changes in time spent affect expected GPA? For example, if you spend 2 more hours per week on study, what is the amount of expected GPAs increased by? One more questions could be, probably the most concerned questions, how to predict your expected GPAs with a specific time span. For example, if I'm going to spend 10 hours per week on study, how to guess my expected GPA? As you can see, it is all about the relation between expected GPAs and time span. To be more specific, you are concerned with the conditional expectations of GPA given time spans per week on study. Actually, conditional expectations is useful when studying the effect of change in conditions in expected outcome. Assumption. For simplicity, we will focus on bivariate distribution to give first insights into the property of conditional expectation. Indeed, in real-life situation, more than one conditions may be involved, and more than one outcome may be expected. Basic notation. Before we study conditional expectation, we have to define some basic notations here. Let x and y be random variable with the marginal distributions fx of x and fy of y respectively. Their joint distribution is fx and y. PDF stands for probability density function, which is used for continuous random variable. PMS stands for probability of mass function, which is used for discrete random variable. Marginal distributions and joint distributions are related by this formula. In truth, the two cases are similar, with summation sign in discrete random variable being replaced by the integration signs in continuous random variable. The formulas are intuitive at all. If we want to find the marginal distributions of x with only x as the random variable, we need to add up all the corresponding cases of y. The same ideas can be applied to the marginal distributions of y. However, what is the meanings of marginal distributions and joint distribution? It is more understandable for the case of discrete random variable. The marginal PMF of x is the probability of x taking the value of small x, and the marginal PMF of y is the probability of y taking the value of small y, while the joint PMF of x and y is the probability of x taking the value of small x and y taking the value of small y. It is more abstract for the case of continuous random variable. The marginal PDF of x and y does not have direct relation to probability, but integrating marginal PDF over an interval does tell us the probability of falling into that interval. Double integrations of joint PDF of x and y over the interval of x and over the interval of y will give us the probability of x and y falling into the corresponding interval. The expectations of x, denoted by E of x, can be found by summing or integrating the product of the values of x and the marginal distributions of x. If the expectation is taken with respect to y, then we have to change the value of small x to that of small y, and the marginal distributions of x to that of y. You may realize that if we have to take expectation to a random variable, we have to know the underlying distributions of that random variable first, and then use it for summations or integration. Therefore, before finding conditional expectations, we have to understand conditional distribution. The conditional distributions of x given y can be calculated by the joint distributions of x and y divided by the marginal distributions of y. The formulas for the two conditional distributions are shown here. Assumption. For simplicity, from now on, we consider only the conditional distributions of x given y, because we could just interchange the row of x and y to get a similar result for the conditional distributions of y given x. Definition. Here comes the formal parts of the conditional expectation. The conditional expectations of x given y is the expectations of x under the conditions of y equals to small y. Recalls the formula of e of x. To find e of x given y instead, we just need to replace the marginal distributions of x in e of x by the conditional distributions of x given y in e of x given y. Basic property. The first property is called a linearity. We can pull out the constant term from the conditional expectation. The proof is quite simple. We prove only continuous case, with discrete case left as exercise. Recall the formula of e of x given y by replacing the value of x by the value of ax plus b. We can then separate the term in integration to get a desired result. The intuition behind is that conditional expectation is a linear operator. The second property is called independence. If x and y are independent, conditional expectations of x given y is the same as the unconditional expectations of x. To prove this, we have to note that if x and y are independent, the joint distributions of x and y is just the product of the marginal distributions of x and the marginal distributions of y. By plugging the above facts into the formula of conditional distribution, we just note that conditional distributions of x given y is the same as the marginal distributions of x. By plotting these facts also into the formula of conditional expectation, work is done. The intuition behind is that if x and y are independent, the value of y does not affect the expected value of x. Example 1. We have already learned some basic definitions and property of conditional expectation. Next, we should apply that in some examples. Let x and y be discrete random variable with joint PML of the form shown. Find c of x given y equal to small y and e of x given y equal to 2. To find conditional expectations of x given y equal to small y, we first tries to guess the conditional distributions of x given y. To guess conditional distribution, it is required to guess the marginal distributions of y before that. That is why we start our procedure by summing up the joint PMS given over all possible value of x. Finally, e of x given y equal to small y is found to be 3y plus 5 over the 2y plus 3. Putting y equal to 2 into the e of x given y equal to small y, e of x given y equal to 2 is found as well to be 11 over 7. Example 2. Let x and y be the continuous random variable with the joint PDF of the form shown. Find e of x given y equal to small y and e of x given y equal to 2. Similarly, we start our procedure by integrating the joint PDF givens over all the possible intervals of x. Then, we guess the marginal distributions of y. After that, conditional distributions of x given y is fine. Finally, e of x given y equal to small y is found to be y over 2. Putting y equal to 2 into the e of x given y equal to small y, e of x given y equal to 2 can be found as well to be 1. Main theory 1. We can now develop our knowledge into some theory. From example 1 and example 2, it is worth noticing that e of x given y equal to small y is a random variable, which is a function of y. That means we can take expectation to the e of x given y equal to small y with respect to y. Interestingly, we get e of x. It is an important theory called the Tower property or the law of total expectation. Note that the inner expectation is taken with respect to x given y, while the outer expectation is taken with respect to y. Proof is given for the purpose of completeness. If x is discrete, the steps are shown here. If x is continuous, the steps are shown here. Example 1. Continuously. Recall that x and y are discrete random variable with the joint PMF of the form shown. Find e of x. By Tower property, e of x is equal to the expected value of the e of x given y. We have found that the marginal distributions of y and the conditional expectations of x given y equal to small y. By putting the above facts into the formula of expectation, e of x is found to be 25 over 16. Example 2. Continuously. Recall that x and y are continuous random variable with the joint PDF of the form shown. Find e of x. Similarly, by the Taylor property, E of x is equal to expected value of the expectations of x given y. We have found the marginal distributions of y and the conditional expectations of x given y equal to small y. By putting the above facts into the formula of expectation, E of x is found to be 1 over 3. Main theory 2. Let x1 up to xn be IID random variables with the common mean E of x. Let n equal to small n be a random variable, independent of all xi's, where n is a positive integer. Random sum means the sum of n's numbers of IID xi's, given that n equal to small n's. Expected value of Sn given n equal to small n is equal to small n times E of x. Replacing the value of small n by the random variable n, we have the conditional expectations of Sn given n. By Taylor property, we can take expectations with respect to n. Eventually, unconditional expectations of Sn is equal to the product of expectations of n and expectations of x. Example 3. Let's see how we can use the random sum theory. Firstly, a fair dice roll, n is the number facing up. Then a fair coin is tossed n time. T is the number of tails obtained. Find expected value of t. Obviously, the distributions of t depends on the conditions of n. If we guess the number of 2, then we can toss the coins 2 times. If we guess the number of 5 instead, we can toss the coins with more times, and the number of tails obtained may be larger too. Our first approach is to use the conditional distribution to find the unconditional expectations of t. However, it is not our focus. The steps are shown here for reference only. As you can see, the answer acquired is 1.75. Our second approach is to use the random sum. If we consider xi to be the number of tails obtained in the ith toss, which means that xi takes the value of 1 if a tail is obtained, while xi takes the value of 0 if head is obtained. Actually, xi follow Bernoulli distributions with probability of 1/2. Because we have the equal chance to get a tail or heads, all xi's are IID since each toss will not affect the next toss. All xi's are independent of n, as the distribution is the same no matter how many times we toss. With all the above satisfied, we can establish the random sum by n's and xi's from the formula. E of Sn is equal to expectations of n times the expectation of x. We get the same result of 1.75. Exercises. Here are some exercises for you to do. Let's see how well you understand the topic. It is the end of this tutorial. Thank you very much.